Welcome to the Illinois Must-Sim Testing Facility, part of the National Science Foundation Network for Earthquake Engineering Simulation.
This facility consists of a 28-foot high L-shaped strong wall and 3 large loading and boundary condition boxes, or LBCBs, that you see behind me here. These LBCBs can impart any combination of 3 rotations and 3 translations on large-scale test structures with almost 1 million pounds force. In the large-scale testing facility, each actuator has a capacity of 328,000 pounds, or 328 kips. The combined vertical force of the 3 actuators is almost 1 million pounds.
Entire systems can be tested using the hybrid methodology through the SIMCor software that enables the full integration of experimental and computational components. The Must-Sim hub of operations is the user's studio that has workstations for visiting researchers, a conference center, and a fully functional 1/5 scale version of the large testing facility.
In this small scale facility, which is exactly 1/5 scale geometrically, each actuator has a capacity of 1 kip, or 1,000 pounds. The maximum vertical force in the small scale facility is 3 kips, or 3,000 pounds.
Prior to using the large laboratory, researchers can test out their ideas and loading protocols in the small-scale laboratory. This has proven to be a great advantage for conducting conclusive and realistic experiments that are made possible by the versatile Must-Sim equipment and control architecture. 3 examples of experiments that have been conducted in the Must-Sim facility are now provided to illustrate some of the exciting capabilities. A multi-site hybrid simulation experiment was conducted of a 4-span bridge structure. 1 pier was tested at Illinois, a second at Lehigh, while the 3rd pier, the superstructure, and the foundation systems were modeled computationally at RPI. In this simulation, the 3 piers supported equal shares of the force from the superstructure. After 10 seconds, there was significant shear cracking of the Illinois pier, and this immediately led to a dramatic shift of loading to the Lehigh pier. The results of this experiment illustrate the importance of conducting system-level investigations as made possible by the Must-Sim hybrid testing capabilities. Another NEES project investigates the behavior of structural concrete walls for high-rise buildings, with experiments on the bottom 3 stories of planar, coupled, C-shaped, and core wall systems. Advanced measurement systems are being used to measure the deformations and cracking patterns on the surface of the test structure to calibrate computational models and to improve performance-based design methods. The Controlled Rocking project at Illinois comprises a series of experiments conducted on steel frames that are connected with fuses to dissipate energy and keep the frame response elastic, and with vertical post-tensioning to self-right the frame at the end of the earthquake. In these tests, a single LBCB was used to impose large displacements on these 18 feet tall frames. The results have illustrated the great potential of this system and helped finalize the design for an upcoming test in Japan.
The features of the Must-Sim facility have been very deliberately designed with the objective of providing the most realistic boundary and loading conditions that brings us very close to reality. If we contrast it with traditional testing, if you like, where we idealize things, we say, for instance, that we cannot account for the interaction between the member and the system, maybe a column within a building. We cannot have a building that is 6 stories high in the lab. Right now, we're actually using the interaction between the experimental setup and the analytical tools that we have and the software that Must-Sim facility has developed. We can indeed virtually test a 6-story building, but we focus on the components of the building that we know are most critical, and these will be tested at full scale, in which case we are really coming not just quite close to reality, but actually we are mimicking reality in terms of the loading and boundary conditions that are imposed on this member as if it was in the building in the field.